Again, you're so much welcome for Muhumuza Naphtali Science.com channel. And as I always tell you that always first subscribe and make sure you watch this video until the end, because that's when you benefit as a medical student. So let us get started. And today we want to look at how do we regulate glucose in the body. We have seen how it is digested. We have seen how it is absorbed and metabolized. Then we want to see how does our body regulate glucose at its normal rate. Because we know in our body glucose is regulated between 70 to 110 milligrams per deciliter. This is for fasting, and it should always be less than 140 milligrams per deciliter. This is for postprandial. This is postprandial. That is random. So we want to see how does our body regulate this glucose at these levels in blood. And we want to see hormones involved in regulation of glucose. Because what regulates glucose majorly, they are hormones. And the major key hormones is insulin and glucagon. But we are also going to see others that regulate this glucose in the body. So listen. So we want to start with what we call hypoglycemic hormones. There are hormones what we call hypoglycemic. Then we shall show also what hyperglycemic hormones do. Hyperglycemic hormones and hypoglycemic hormones. Let's start with hypoglycemic hormones. Hypoglycemic hormones. We want to look at hormones which reduce blood glucose levels in our body. Those are what we call hypoglycemic. But in case glucose is high, which hormones reduce it to normal? Those are what we call hypoglycemic hormones. And one example of hypoglycemic hormone is insulin. And this is the major one. This is the major hormone which is responsible for reducing. This one acts by reduces blood glucose levels. Blood glucose levels. And as we said that this insulin is produced by beta cells of the pancreas. And we said when these beta cells, what triggers beta cells to release insulin is high levels. It is triggered, its production is triggered by high levels of glucose in blood. And once released, insulin, we said it comes and enables entry. We said we have the GLUT2 transporters on the liver, and when insulin released, insulin is the one that enables this is our glucose. We shall see insulin leading to opening of the gates on the GLUT transporters, enabling entry of glucose into cells. Then the glucose is able to enter into cells. That's the role of insulin. So that's why we say insulin acts by lowering blood glucose levels. It reduces blood glucose levels, but it increases tissue glucose levels. It reduces glucose levels in blood, but increases it in tissues or cells. Do we get that? In blood, it is lowering it, but in tissues, because it is causing it to enter into cells, so it will increase the sugar concentrations in the cells. That is the role of insulin. And this insulin has many functions. We want to look at the functions of insulin. After enabling entry of glucose, this insulin stimulates, apart from enabling entry of glucose in cells, it stimulates glycolysis. It stimulates glycogenesis. It also stimulates lipogenesis. It stimulates lipogenesis. And all these processes act by lowering blood sugar levels. Whereby glycolysis, we said, is conversion of glucose to pyruvate. Then glycogenesis is conversion of glucose into glycogen. Then lipogenesis, conversion of glucose into lipids. Then it also inhibits reactions like it inhibits any process that increases blood sugar levels. And we know these processes like gluconeogenesis. It goes and it inhibits gluconeogenesis, whereby gluconeogenesis is the formation of glucose from non-carbohydrate sources. It inhibits formation of glucose from non-carbohydrate sources. Non-carbohydrate sources like proteins, like lipids. It also inhibits glycogenolysis. It inhibits glycogenolysis, that is breakdown of glycogen to glucose. Because when these processes occur, they increase blood sugar levels. And the main aim of this enzyme, of this hormone, is to reduce sugar levels. So it also inhibits lipolysis. Lipolysis is breakdown of lipids into fatty acids and glycerol. And we know that these fatty acids and glycerol, because for example, glycerol can be used by the process of gluconeogenesis to bring more glucose. So insulin stimulates these three processes and inhibits these three processes. I've said it stimulates glycolysis, glycogenesis, lipogenesis, then inhibits gluconeogenesis, which is the formation of glucose from non-carbohydrate sources, glycogenolysis, which is breakdown of glycogen to glucose, then lipolysis, which is breakdown of fats into free fatty acids and glycerol. That is the role of insulin in the body. Don't forget that it is produced by beta cells in response to high levels of what? Glucose. And we see in biochemistry, you would have looked at how is insulin synthesized, isn't it? In the beta cells. That if we have beta cells on the pancreas, the precursor is called pre-proinsulin. Pre-proinsulin. And this pre-proinsulin, we know that insulin, this one is always in hexamer form. It is a hexamer. And the active one is always a monomer. The active form of insulin is a monomer. So when we have proinsulin, it is converted into proinsulin. This is we are in the rough endoplasmic reticulum. In the rough endoplasmic reticulum, we have proinsulin being converted to proinsulin. And this proinsulin is done, it occurs in the presence of signal recognition peptide. Signal recognition peptide is the one that cleaves off this, which converts this hexameric form of pre-proinsulin to proinsulin, isn't it? Then when we have proinsulin goes into the endoplasmic reticulum and it is converted into two things. We get what we call insulin and C-peptide, isn't it? So, and these ones are always produced in equal portions. When insulin is 10, even the C-peptide has to be 10, isn't it? They're always in equal amounts. So if and we know in lab in Uganda here, we cannot measure insulin, but we can easily measure C-peptide. So if I want to diagnose diabetes type 1, I can do C-peptide assay. If I find the C-peptide is much, it will also tell me that insulin is too much. That one means that is diabetes type 2. But if I do C-peptide assay, I find it is not there in the blood, means also insulin is not there. It can confirm me diabetes type 1, which is insulin dependent, isn't it? So we can always do C-peptide assay. So when we have proinsulin, it is the one that is converted to. And we said the active form of insulin is, it is the monomer. Active insulin is always in monomeric form. Monomeric form is the active one. So you will read about that biosynthesis of insulin in the beta cells, and also go ahead and look at what triggers beta cells to release insulin. The first thing we have looked at is increased levels of glucose. You will also look at how glucokinase can also stimulate production of insulin from the beta cells. So this is what I can tell you about insulin, our dear insulin. So what you cannot forget about insulin is the one that enables entry of glucose in cells. And we have gone to look at the difference whereby it stimulates these processes and inhibits these processes. Then later, we have even tried to look at how it is synthesized. And after being synthesized, it is stored in the secretory vesicles. You know, in the Golgi apparatus, from the rough endoplasmic reticulum, you will go to the Golgi apparatus, then to the secretory vesicles. You remember the endomembrane system of the cell. I think it was not easy. It was really work. So this is what we call a hypoglycemic hormone. For it, it is triggered by hyperglycemia. That's why we said increase in sugar level is what we call hyperglycemia. When there is hyperglycemia triggers beta cells to release insulin, and this insulin is the one that is enabling entry. Then enabling all these processes, and we have seen how it can be synthesized. And we can say, we have said, we can do C-peptide assay to distinguish between diabetes type 1 and type 2. Whenever we find there is low C-peptide or no peptide, no C-peptide, that one confirms type 1. Because we have said C-peptide and insulin are produced in equal proportions, isn't it? That is the end, that is the hypoglycemic. So now we can look at the hyperglycemic hormones. Hyperglycemic hormones. These are hormones that when there is low blood sugar levels are triggered to increase blood sugar levels. So the trigger factor here is hypoglycemia. Hypoglycemia is the trigger, or it is the one that stimulates the production of hyperglycemic hormones. When there is low blood sugar levels, triggers the production of hyperglycemic hormones, and the role of hyperglycemic hormones is to do what? To increase. So when they are produced, they are the one that increase blood sugar levels. This one is increased blood sugar levels. And these hormones include, we are seeing, they include, the chief of all is glucagon hormone. Then we can have other hormones like thyroxine, which we normally abbreviate it as T4. We shall have other hormones like epinephrine. We shall have another like cortisol. Then we have ACTH, adrenocorticoid hormone. That is ACTH. Then we can have growth hormones. Growth hormones are also part of hypoglycemic hormones. We can even have somatomedins, but we know that growth hormones work through somatomedins. So these are the major hyperglycemic hormones that act by increasing blood sugar levels. So we want to see the function of each. The first thing is to know where is it produced and what is its function. So we can even draw a table here. We can draw a table. We look at the role of glucagon, we look at the role of thyroxine, the role of epinephrine, cortisol, and ACTH, then the growth hormone, and then somatomedins. But before we look at the function, the first thing is the site. So we have a hormone, We have the site of production. Then we have also the function as pertaining glucose regulation. So glucagon, being antagonistic to insulin, for it is produced by the alpha cells of pancreas. And it is the trigger factor is the hyperglycemia, or that is a decrease in sugar levels, which stimulates the alpha cells to release glucagon. And this glucagon, when once produced, it does the opposite work. What insulin was stimulating, glucagon is going to inhibit. What insulin was inhibiting, it is going to stimulate. But we see glucagon majorly, it stimulates both glycogenolysis and gluconeogenesis. It stimulates both glycogenolysis, that is breakdown of glycogen to glucose, and gluconeogenesis, which is the formation of glucose from non-carbohydrate sources. That is the role. And it does the same role with the thyroxine. Thyroxine also stimulates both glycogenolysis and gluconeogenesis. But let us not forget about this one, can also stimulate lipolysis. Glucagon can also stimulate what? Lipolysis. Even this can stimulate lipolysis, apart from glycogenolysis and gluconeogenesis. Are we together? So, another function, another enzyme, where is the thyroxine produced? It is produced by the follicular cells. Follicular cells of the thyroid gland. So it is produced by the thyroid gland, and its role is to stimulate glycogenolysis and gluconeogenesis. Then epinephrine, you remember the catecholamines in endocrinology, whereby we had epinephrine and norepinephrine. So this epinephrine is produced by the adrenal medulla. And its role, for it stimulates glycogenolysis. Not gluconeogenesis, glycogenolysis. And it can also go ahead to stimulate lipolysis. But not gluconeogenesis. Hope all of us we are writing. Please just write summary, so that always when you're watching these videos, make sure you write something so that it can help you when you are done with watching. Then cortisol is a glucocorticoid. And this glucocorticoid hormone is produced by the adrenal cortex, isn't it? Adrenal cortex. And this adrenal gland is found on the top of the kidney. Just it always lies on the top of the kidney, which is divided into adrenal medulla and adrenal cortex. And this cortisol, it is also responsible for, it stimulates gluconeogenesis. Gluconeogenesis. And also it can enhance absorption of glucose. It enhances or increases absorption of glucose. So apart from initiating gluconeogenesis, it also makes sure that every glucose that is formed in the intestines is absorbed, because their role is to increase sugar levels. Then this adrenocorticotropic hormone, for the adrenocorticotropic hormone is produced by the anterior pituitary gland. Anterior pituitary gland. Then this growth hormone for it is also produced by the anterior pituitary gland. Then somatomedin is produced by the liver. And all these do the same role of cortisol. They all stimulate one is gluconeogenesis and increase absorption of glucose from the ileum. Hence, they are able to increase blood sugar levels. And this one, they like it so much. They like it so much in objectives and in section B. We can easily ask you outline at least two functions of each hormone, or outline hyperglycemic hormones. Or we can say the following are hyperglycemic hormones except. So you must know what hyperglycemic is. And the better thing is to know what triggers them. That is decrease in sugar levels. And after being triggered, their role is to increase blood sugar levels through these processes we have outlined down. These are the processes. And we are saying, kutoka hapa kufika huku, from here, from cortisol to somatomedin, all of them are doing the same role. Enhancing gluconeogenesis and increase blood sugar level absorption from the intestines. That is from the ileum. So that is how the body controls. So whenever the blood sugar level goes above 110 for fasting and above 140 for postprandial, insulin is produced, isn't it? Then whenever sugar levels go below 70 for fasting and I think it's below 126 for postprandial, then we see the hyperglycemic hormones coming in. And all of them work together to ensure sugar levels remain at a constant or at a normal range. That is how glucose levels are regulated in the body. And any failure of this regulation, especially when the insulin is not doing well, that's when it can result into hyperglycemia, isn't it? We can get conditions like hyperglycemia, which we are going to talk about in the next video, that can get a condition called as hyperglycemia or hypoglycemia, whereby hyperglycemia is increased sugar levels beyond, let me use even another color, beyond 11.1 millimoles per liter, or what we can say beyond this one. When it is converted to milligrams per deciliter, it becomes 200 milligrams per deciliter. Then hypoglycemia is decrease in sugar levels in blood, sugar levels below, let me use another color, below 3.6. Some books say below 3.6 millimoles per liter. Or sometimes Michael L. Bishops, in his book of clinical chemistry, he says 4.5. Some books can give you 4.5 millimoles per liter. So whenever you are defining hyperglycemia or hypoglycemia, you must give me the reference, the range, the cutoff. That's how it comes out. So thank you so much for listening about the regulation of glucose levels. Please always keep updated or keep subscribing so that you can always be updated with the videos we release. I remain Muhumuza Naphtali.com here in Uganda, in Murago.